Salam and peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning together? There is one field called phi, spelled Phi. Phi is the holophase, a cyclic rhythm defined at every point in the universe. Its first derivatives give three simultaneous echoes: time, which we call omega, spelled Omega, space, which we call k, and motion, which we call v, built from both omega and k. Above them, higher derivatives form a branching tree that in principle goes on forever. Every law of nature is a pattern in this tree of derivatives of phi. Today, we zoom into just one branch of that tree. In part 17, we stood at one tiny point in reality and asked the big question. If we knew not just what phi is doing there, but how it is changing, and how the change itself is changing, and so on, how much of the nearby world could we predict? We met the infinite dictionary of the holophase, the jet, which is like a complete local description of how patterns want to unfold around the point. Today, in part 18, we do something very different. Instead of asking, what is the local dictionary here? We ask, what kind of pattern is this as a whole? Is it knotted? Is it twisted? Could you ever smooth it away? In other words, we step from local grammar to global shape. We move from what is happening right here to what kind of thing is this, no matter how you shake it. This is the part of the holophase language where particles, charges, and many solid things first begin to appear as stable words in the phase code. But we will not begin with particles. We will begin with something you already know very well: knots, loops, and holes. I want you to imagine that you are holding a long rope in your hands. You let it hang loosely, then slowly tie a simple overhand knot in the middle. You pull it tight. Now ask yourself a very simple question. What is the difference between the knotted rope and the unknotted rope? If you look very closely at the material of the rope, at the fibers, at the color, nothing fundamental has changed. It is the same rope. What has changed is the way the rope is arranged in space. Some parts pass over and under others. There is a loop that traps itself. If you try to undo the knot without cheating, without cutting the rope, you will discover that you cannot. The configuration belongs to a different type than the loose rope. Already, you are touching the heart of part 18. A knot is not a new substance. It is a special arrangement that cannot be undone without tearing or cutting. It is a pattern that is stable under smooth deformations. You can wiggle the rope, stretch it, twist it, but as long as you do not cut or glue, the fact knotted versus unknotted stays the same. This kind of property is called topological. You do not need the word. You already know the idea. Two things are topologically the same if you can smoothly reshape one into the other without cutting or gluing. A coffee mug with one handle and a donut with one hole are the same in this sense: one hole. A plate has no holes. A pretzel might have 3 holes. You cannot turn a donut into a plate by stretching. You would have to tear out the hole. Now imagine that instead of a rope, you have the phase field phi, living everywhere in space. At each point in space, phi has a value. You can think of it as an arrow that points somewhere on a circle, or a hand on a clock that can be at any angle from 0 to 360 degrees. As you move through space, this hand can rotate. Sometimes it rotates gently. Sometimes it turns many times as you loop around some point. Here is the key idea of this part. In the holophase universe, you can get knots not in the material itself, but in how phi wins as you walk around certain regions. These are knots in the pattern, not knots in the stuff. They are topological defects in the phase, and they are the seeds of what we later call particles and charges. Let us make this very concrete. Imagine you are walking in a circle around some invisible center in space. At each step, you look at an arrow painted in the air showing the local value of phi. You start at some angle. As you walk around once, you watch the arrow rotate. If, by the time you have gone full circle, the arrow has turned exactly once, making one full rotation, we say the winding number of phi around that loop is +1. If it has turned twice, it is +2. If it has turned backwards once, it is -1, and so on. You do not have to remember the numbers, just remember the image. You walk around the loop and you count how many times the phase angle goes all the way around its own circle while you go around in space. Now, here is the surprising part. Once that winding is present, you cannot get rid of it by gently deforming the pattern. As long as you do not cut space open, and as long as phi stays smooth everywhere on your loop, the number of turns you counted is fixed. It is like the knot in the rope. You can jiggle it, stretch it, squash it, but its basic count does not change. In the codex, we collect all the places where phi cannot be made smooth, or where you cannot assign a phase consistently around the loop, into a set called sigma, written as the Greek letter sigma. You can hear it as the defect skeleton. Sigma is the set of points, lines, or surfaces where the phase language breaks, where the code has a singularity. Around sigma, you can have these windings. Let us slow this down with an everyday analogy. Picture a city map seen from above. You draw a small circle on the map, representing a walk you might take around the block. Now, instead of arrows of phase, imagine that at each corner, someone is playing a note on a violin. As you walk around the circle, the note might slowly rise in pitch, go up an octave, and then come back to the original note as you return to your starting point. If, after one loop, the music has gone up by a whole octave and returned to the same named note, you can say loosely that the musical phase has wound once. If you went around and the note came back twice as high, 2 octaves, you could say it wound twice. Now suppose that no matter how the musicians change their style, as long as they play smoothly and continuously while you walk, that total winding, how many times the tone climbs and lands back in the same slot, stays the same. That would be a topological property of the musical pattern around that block. In the holophase picture, the musicians are not real. They are a metaphor for the phase angle of phi. The block you walk around is a loop in space. The places in the city where no musician stands, or where the sound is undefined, are like defects. Around those places, the phase can wind. Why does this connect to particles? Because a winding number behaves in exactly the way that many conserved quantities in physics behave. It is robust. You cannot change it in small steps. You cannot have half a winding in certain situations. You either have 0 or +1 or -1. To change it, you must do something dramatic. Let two defects meet and annihilate, or tear the pattern. Think of a pair of shoelaces, each tied into a knot. One left-handed, one right-handed. If you bring them together in the right way and pull, they can untie each other and leave you with two loose laces. In the phase story, a defect with winding +1 can meet a defect with winding -1 and disappear, turning into a smooth field. The charge has been neutralized. This is not just a metaphor. It is the direct, testable behavior of many real systems with phase-like fields, from vortices in fluids to defects in liquid crystals to certain excitations in quantum fields. Let us talk about a very familiar example, a whirlpool in water. When you pull the plug in a bathtub, a vortex often forms. Water spins around the central core and drains. If you put a tiny leaf on the surface, it circles around, not just moving, but rotating around an invisible line. That central line is a defect. At its center, the water's velocity is undefined, and the phase of the flow goes wild. If you walk in a circle around that line, following the leaf, you would find that the direction of motion has rotated by a full circle as well. That is a winding. You can disturb the water, splash it, stir it. The exact shape of the whirlpool may change, but as long as the vortex core persists, the once around nature of the flow remains. To get rid of the whirlpool, you must either bring in another whirlpool, spinning the opposite way, and let them cancel, or you must slow the flow so much that the defect line collapses. In holophase language, that vortex is a knot in the phase field phi. The winding number around the vortex is what makes it topologically stable, what makes it more than just some movement. The same story appears in superfluids, in superconductors, in certain kinds of magnets, and in the patterns of light itself. Measurable, quantized vortices appear, whose strength is given by integers, because underlying them is a phase that must return to itself after a full loop. The holophase approach simply raises this familiar pattern to the status of the basic code of reality. Where does sigma, the defect set, enter? Imagine all the points in space where phi is well defined, where the hand of the phase clock has a clear angle. These points form the smooth fabric of the code. Now mark all the places where this is not true, where you would have to say, here the phase is undefined, or jumps in a way that cannot be smoothed. These marked places form sigma. Around lines or surfaces in sigma, the phase may wind. You do not have to picture it as formulas. Picture it as a web of possible vortices and knots. Sigma is like the hidden skeleton of the code. The rest of space is like the flesh. When you walk in a loop that encloses part of sigma, you can detect its presence by the way phi winds. You do not see sigma directly. You infer it by the patterns of phase around it. In physics, this is exactly how we infer charges and particles. We rarely see a charge as a little ball. We see its effect on the surrounding field. Now, let us speak about falsifiability. How could someone test whether this topological node-based view of matter and charge has any truth to it? Here is a simple operational story. Suppose you have a system where you can measure a phase. For example, a ring of superconducting material, a thin film of superfluid helium, or an optical beam with a controlled phase profile. In all these cases, the phase winds around some loop, and the winding number is integer valued. You prepare the system in a state with winding number +1. Operationally, that might mean that the supercurrent around the ring corresponds to one quantum of magnetic flux, or that the optical phase wraps once around the beam. Now you gently disturb the system. Hit it slightly, bump it, apply smooth fields. If the holophase language is right, and this is truly a topological defect, the winding number should not change under any small, smooth disturbance. Only when you drive the system through a transition where the order itself breaks, for instance, warming it past a critical temperature, should the winding be able to vanish. You can measure this. You can watch the quantized flux or the vortex count before and after. If it jumps by fractions or smoothly drifts, the topological picture fails. If it only changes in integer steps and under specific violent operations, that is supporting evidence. The holophase program goes further and says, at a deeper level, all charges in nature are like this. Each charge is a way that phi winds around some subset of sigma. Sigma may be lines, like strings, points, like monopoles, or more exotic shapes, depending on the context. But the logic is the same. Walk around, count the turns, get an integer, and that integer is a label of a durable, particle-like pattern. Let us return to an extremely simple picture to keep this grounded. Imagine you have a rubber sheet with arrows drawn on it, each arrow showing the direction of phi. In most places, the arrows change smoothly. Now pick a point on the sheet where, as you walk in a circle around that point, the arrows rotate by a full spin. That point is a defect. If you try to erase the arrows and redraw them smoothly to remove the twist, you will find that you cannot do it without erasing the defect point itself or tearing the sheet. If you have two such defect points, one with arrows spinning clockwise, one with arrows spinning counterclockwise, you can bring them together. As they merge, the arrows around them can gradually straighten out until there is no net twist left. The defects annihilate. You have just watched a +1 and a -1 winding meet to make 0. No new material has appeared or disappeared. Only the arrangement has changed. This picture is both simple and powerful. It tells you that the universe can store information not only in local values, phi at a point, or in derivatives, how phi changes, but also in global topological numbers. How many twists exist, in what sense, and where. These numbers are robust, discrete, and naturally associated with particle number, charge, and similar concepts. In the Holophase language tree, this whole topological story is one big branch, labeled by sigma, the defect set, and by winding numbers around it. It is not a separate ingredient added on top of the field. It is just a higher level property of the same phase field you have already met. The rope, the knot, and the smooth parts are all the same rope. Before we close part 18, I want you to feel how this changes your way of seeing. The next time you stir your tea and see a tiny whirlpool form, you can whisper to yourself, "There is a little piece of sigma in my cup, a defect line in the phase of the fluid." When you see the pattern on a tightly woven rug, small motifs repeating with little twists and crossings, you can think, here are phase patterns wrapping around holes in the weave. When you watch two smoke rings collide and break apart in the air in slow motion, you are seeing knots in a field interact. And you, as a human being, are not separate from this. Your body is made of countless stable patterns, from electrons to atoms to molecules to cells. Many of these can be understood as excitations and defects in underlying fields, each with their own winding-like labels. In the holophase picture, there are all different words written in the one-phase language. You do not need to know the formal equations to participate in this. The falsifiable content is there for the laboratories and the papers. For you as a listener, what matters is that you can now entertain a very simple but deep possibility. That what we call a thing, a particle, a charge, a vortex, a knot, is really a way that the one underlying rhythm of the universe, phi, has tied itself into a pattern that cannot be undone without crossing a topological line. In later parts, we will connect this topological view to forces, to energy, to information, and to meaning. But here, at the level of the alphabet of the holophase language, part 18 teaches us one crucial letter, the letter of knots. It says, not all patterns are alike. Some can be smoothed away, and some are knotted. Those knotted patterns are the ones that behave like stable nouns in the sentence of reality. As you move through your day after this episode, I invite you to notice knots and holes. Notice the ring of your mug, the loop of your belt, the spiral in your fingerprints, the little whirlwinds of dust in the street. Each one is a gentle reminder that the universe loves to twist and loop, and that these topological features are not accidents. In the holophase view, they are part of the very language from which everything is written. We began with a simple rope in your hands. We end with the entire cosmos as a woven fabric of phase, full of knots and loops, all encoded in the derivatives of one field, phi. In between lies the bridge from a child's game of tying knots to the most precise experiments in modern physics. That bridge is topology, the science of shape that does not care about distances, only about how things are connected. Let us spend a little more time with everyday scenes, so that this does not remain an abstract picture in your mind. Imagine you are looking at a sink full of water. You pull the plug, and the whirlpool forms. Now imagine yourself as a tiny explorer, small enough to walk on the surface of the water without sinking. You decide to walk a perfect circle around the whirlpool, always staying the same distance from the center. At every step, you look at the direction of the flow right under your feet. At first, it points to your right. A little further along, it points diagonally behind you. A little further, it points directly backwards. After you complete the circle, you have seen the flow direction rotate all the way around. If you could draw an arrow for each step, and then look at that ring of arrows from above, you would see that they twist once around the loop. Now ask a sharp question. Could you erase the whirlpool by just gently stirring the water in some clever way, without ever creating a second whirlpool or stopping the drainage? Try to imagine it in your mind. As long as the water is draining and that central hole in the flow exists, the twisting must be there. This must is what we mean by a topological constraint. The global situation, water leaving through a single drain, forces a certain kind of winding in the pattern. In the holophase universe, sigma is like the collection of all such drain lines and hole points in the abstract phase fabric. You never touch sigma directly. You walk around it. You measure the twisting of phi. You infer that there is a defect there, just as you infer a drain in the sink from the circling of the water, even if it is covered by bubbles. Here is another picture, using roads. Imagine a roundabout, a circular road junction. Cars enter and leave, but the central island is never driven on. If you stand at the edge and watch the flow of cars, you can see a clear once around pattern. The central island plays the role of sigma. It is the region that traffic never occupies, the hole around which motion winds. If you changed all the cars to bicycles or to people jogging, the flow would still wind around the central island. The details of the traffic do not matter. The existence of the island does. In the phase story, the traffic is the way phi changes. Different physical systems give different kinds of traffic, but the underlying whole is the same topological fact. Around some regions, the phase must twist. Those twists can be counted. Those counts can stay fixed for a very long time. You might wonder, is this really about the deep universe? Or is it just a pretty way to talk about fluids and traffic? The falsifiable claim is this. Whenever you have a system where the basic quantity is a phase defined on a circle, something that must come back to itself after a full turn, and whenever there is a region where that phase cannot be defined smoothly, you should expect integer winding numbers around that region. Those integers should be remarkably stable and should behave like conserved charges. This is a concrete prediction. It has already been checked in many systems. The Holophase program dares to say that this pattern is not an accident of those particular materials, but a window into the fundamental language of reality. Let us also talk about dimensions, but gently. In three-dimensional space, defects can look different depending on their shape. A point defect is like a tiny speck. If you walk around it in any loop that encloses it, the phase may wind. A line defect is like a thread running through space. Loops that encircle the thread can pick up a winding, but loops that miss it do not. A surface defect is like a sheet. If you cross it, the phase may jump in a controlled way. You do not need to memorize this catalog. What matters is the idea that sigma can be made of different bones, points, lines, sheets. Around each kind, different kinds of winding are possible. The Holophase Codex treats all of these in one unified language, organizing them as different letters in the topological alphabet. Some letters correspond to point-like charges, some to string-like objects, some to wall-like structures. But in every case, we are not adding new substances. We are reusing the same phase field phi and asking, how is it not at this time? Let us turn to one more experiment you can imagine, even if you never perform it in a lab. Consider a very narrow ring made of a special material that supports a phase. For instance, a superconducting ring. Around this ring, the phase must return to the same value after a full circle, just like the water flow direction did around the drain. Because of quantum rules, the allowed patterns for the phase around the ring come in discrete steps. You can have no twist, one twist, two twists, and so on. Each twist pattern corresponds to a different current circulating in the ring, and each current corresponds to an integer amount of magnetic flux. Experiments show that the magnetic flux through such a ring comes in exact chunks, never in arbitrary fractions. That chunking is a fingerprint of a winding number. In the holophase interpretation, you would say, the phase around the ring has a topological winding, labeled by an integer. The physical observable, the current, the flux, is a readout of this topological number. If you slowly adjust the external conditions, the system does not drift from twist number 1 to twist number 1.3. It stays at 1 until, at some critical threshold, it jumps to 2 or back to 0. Jumps between integers, not drifts. That behavior is a test of the topological picture. Even if you never handle superconductors, you can feel the logic. Think of a staircase. You can stand on step 0, step 1, step 2, and so on. You cannot stand at step 1.3 if the steps are rigid and well-defined. To change your step number, you must pick up your foot and move it to a different step. Gentle swaying will not do it. Winding numbers are like step numbers in the configuration space of the phase. They change by jumps, not slides. From a language perspective, this is fascinating. Up to now, many of the holophase quantities we discussed, like omega and k, were continuous. They could take a range of values. But with winding numbers, we meet genuinely discrete letters in the language. A defect can carry +1, +2, -1, and so on. You can sometimes combine them. +1 and +2 can merge into +3. +1 and -1 can cancel into 0. It really starts to look like arithmetic of charges written in the medium of phase. Think of children trading marbles. A red marble might represent a +1 defect. A blue marble might represent a -1. If one child gives a red marble to another, the first child's charge decreases by 1, the second child's increases by 1. If a child has one red and one blue marble and puts them back in the bag together, they can cancel in some game rule sense. The net pattern returns to neutral. In the holophase picture, sigma and its windings play a similar game, but in the continuous phase fabric of the universe.